record. So, okay. So I mix between different environments here. So it's time for the lecture in industrial communication. And I've forgotten that it should be in English. So I will translate the slides later on. Many of the terms are similar. So I think it's fairly understandable, and pictures are fairly understandable, actually. So what was the plan for today and also for next week? It's repeating a little bit about the course, listing some material to read for my part of the course. And then today it will be about industrial communication, field buses and things like that. Next week, it will be more IoT, Internet of Things, and some new technique, new technology. On next week, I will also introduce this poster project a bit. That's the plan. But as a reminder, what was the course about? Let's see, I have the course PM here. It's on Canvas, so it's no surprise and it's no change. But just as a reminder, you have been listening to Andreas, hopefully, and you have done some robot stuff now. I have a little bit part. It's 2 lectures here about industrial communication and IoT, and a discussion on the poster project. Then next week, it will be focus on the CAN bus and the car industry with Erik Lind from, he's consultant and working in the car industry. An old-time teacher. He has been teaching here for some years ago. Next, we have Mats with the wireless communication and some positioning lab, and then it's the poster project the remaining time. But there is a written exam, so it's a little bit important of, we don't have a book for the course, but we actually have some material, and mainly for my parts, it's a lecture slides. I will put up them later on and translate them. But otherwise, I have links to 2 papers or articles here, white papers, that I think is interesting and that you should read. That's part of the course. And I have some pictures from both of them. So the first one is a little bit about industrial communication, but also the future, the next generation Ethernet, industrial IoT and 5G. And then it's a white paper on 5G and how they think that 5G will help factories. So both of these papers are or articles are interesting. But yes, what is it about? Well, it's about mainly the whole course is about industrial control systems, but not really. It's all kinds of industrial communication. So it's also like, for example, we deal with the CAN bus and the car industry as well. But the main focus is really maybe these kind of factory systems here. And we usually distinguish between different parts here. We have the production network, and where you find the small computers that really interact and control stuff, like a robot and things like that. And you have the PLC, programmable logic computer, that's probably what it stands for. That's a typical, it's like a normal computer, but with a lot of IO, input, outputs, and a very robust and slightly more expensive as well, to be easy to install in a factory environment. but there is usually a lot of different PLCs controlling and measuring things in the factory. And but that's the actual, well, that's where things move and the action is. But further up in some kind of hierarchy here, you have a supervision network, or SCADA system. And SCADA is an abbreviation for supervision and control, really. So that's typically systems that interact with the PLC, asks for information, displays nice diagrams, and you might sometimes have humans staring at a lot of screens to see if the factory runs okay. And but it's both ways. So you can typically control stuff. You can press a button here maybe to shut down the factory and things like that. So that's the supervision and control network. And at the top, we also have business systems like ERP systems. That's enterprise resource planning systems, databases keeping track of parts, ordering systems, yeah, economics, all kinds of things at the top. And yeah, so on the left side here, you typically will find normal computers and normal networks. It's normal Ethernet, maybe, or some normal Wi-Fi networks. But at the far right, you have fairly special communication buses. That's where you find the field buses. So these devices and networks differ a lot from what we might be used to. And yeah. So what's the typical requirements, is special requirements here for these kind of automation communication? Well, it's really two main things. It should be robust and protected from noise, or that's a tricky word, störning. Yeah. So it should be able to handle the rough environment in a factory with a lot of
do you mean disturbance? Like
yeah, it's disturbance, but it's more like electrical interference. Maybe it's the right English word. But that's and that's on the electrical level. So you need robust cables and things like that. And yeah. But then on a more logic level, you also very often have time critical traffic, and you need the traffic to be deterministic. When you control things like a robot, you very often have quite tight loops. So you need to be able to guarantee that a packet you sent should be delivered within a certain number of milliseconds or something. So it can be quite tight timing requirements. And that means that it's difficult to use like normal office equipment and normal Ethernet to actually control the robots and things like that. You need special communication buses and technology. And today you have quite a lot of different of these field buses, the different communication technologies. Each company has typically invented their own, and you have many different today. The last 10 years, more and more have been trying to look at normal Ethernet. That's a very widespread technique because that's the normal internet technology that we have everywhere. So if you could use Ethernet even in the time sensitive parts, it would save money, really. And it's more well used and well known. So many field buses have introduced variants that they can run on normal Ethernet as well, but it's not normal, but it's their special kind of Ethernet sometimes. And there are some new technologies. Some things you read about today is the TSN, time-sensitive networking, which is a new approach of using Ethernet in the factory and in time-critical applications. You also have a lot of wireless techniques and the 5G. The next future mobile network should take care of all communication needs. That's what the operators or mobile manufacturers think. It should be able to cover everything. Maybe, we'll see. I don't think today 5G has not solved everything, but well, they might do in the future. Yes, so there is very often requirements of determinism or real time, and it's a little bit different. They are related, but determinism means that you have predictable communication, and you typically want communication in many systems are cyclical. So you for example send a packet each 5 milliseconds, and you state that the variation in receive time shouldn't be more than 10 microseconds, for example. So it should be regular, and when you send it, it should not get disturbed in some way or delayed in some way. That's the jitter requirement. This is really very common, and this is kind of determinism that you can be sure that the system works and does the same thing each time. So you can rely on it in some way. It's quite related to real-time systems, but here you have, it's more important with upper limits for the response times. And sometimes you distinguish between soft and hard real-time. So for soft, it's if you miss a deadline, if it's a packet that arrives late, it's not that critical. The system will keep running, and it's kind of degraded performance only. But in a hard real time, something bad happens. If you miss a packet, or if it's a packet that arrives late, the system will stop working in some way. Hopefully it won't crash or harm people, but that might be the case sometimes. If an airplane control computer stops or misses some deadlines, it could actually be quite catastrophic. So you don't want that to happen. So sometimes you have hard and soft dead real time, and you very often combine it with requirements on determinism as well. That you should, it makes the system more easy to reason about, test, and build sometimes. But you can actually have real-time requirements, but still have not so deterministic system. You can have a lot of jitter, uncertainties, but you will still meet your soft deadlines maybe. So it's not exactly the same.
Sorry, what is jitter?
Jitter is the variation in the receive time.
Okay.
So maybe the next picture is good for that. Yes. So for a whole system, it might look like this, that you have a distributed system with a lot of computer nodes. This could be a PLC controller or whatever. It could be normal computers. It could be computers inside a car. And you might have a sensor somewhere that one computer reads, and then it sends a packet to other computers that should control something. So here, the sensor could be the brake pedal, and the other computers could be the brake in the car that it should, the driver wants to brake. So then you very often have a end-to-end deadline here. The time from when you do something here shouldn't exceed some maximum time, like a certain number of milliseconds, for example, before the system reacts in the other end. And when you design this kind of system, it's very convenient to break down. If you have a 10 millisecond requirement for the whole thing, you might set individual requirements for the different deadlines when you build the computers and communication network and things like that. So this computer gets 2 milliseconds time. The communication must finish within 5 milliseconds, and then you have a certain time budget for the last computers here. That's very common when you design system, that you tell the software developers for computer A here that you have 2 milliseconds to read the sensor and send the packet. That's it. And you must prove that you can meet these deadlines. That's a very important thing, or way of handling things. So what is jitter? Well, jitter is typically you have cyclical systems. So it's this sensor here is it's read regularly with a certain sample frequency, like 20 times per second, maybe. And that's the typical communication cycle for the whole system. That means you every, let's see, like 5 milliseconds, you send a new packet here. If the packet is received here at exactly the same time, each cycle, you have a jitter of 0. It's perfectly deterministic in some way. And jitter of 0 means that it's exactly the same receive time each time. But very often you have communication networks that kind of have queues. You send, you have traffic going, you have competing traffic. So some packets might get delayed. And then you will have a different receive time here, and that's the jitter. So if you have a jitter of 1 millisecond, that means the receive time here can vary by one millisecond. Sometimes the jitter doesn't really matter. Sometimes it's very important that it's not, that the jitter is very low. And if you, it depends on the traffic and the system. If the jitter is less than the cycle time, it's often not so troublesome. But if it's greater than the cycle time, then a later packet can overwrite an earlier packet, and that's not good at all. So the jitter should be, well, not too high, probably. And if you have very high jitter, it's not really a deterministic system. You don't know what will happen. Yeah. So how do you build these things? If you have a requirement on response times or determinism, and you are free to design your network yourself, how should you design the network? How should you send packets and things? Well, we are very used to the normal internet. That's a best effort network. We just send a packet and hope for the best. On the global internet, no packets are directly. It's no priorities. Well, there are actually, but you cannot control it as an end user. When you fetch something from a web page, you actually have to wait until it's finished. You cannot ask for having a higher priority of your traffic or something. And the determinism on normal global internet is very bad. Sometimes you get the web page really fast. Sometimes it will take forever. And that's not good for these time critical networks. You want to be able to guarantee some kind of determinism here. And there are two main ways of solving this, two different techniques in some way. So one way is having this kind of cyclical system, and it's time controlled with time slots. So you have a schedule, and each kind of node or traffic flow needs to reserve some time slots where they are allowed to send things. And this means that you have each node that wants to communicate have their exact time slot, and they know, and you can, when you design the system, you know really well when all packets will be sent. There are time slots reserved for all traffic. And if you have a long cyclic time, you can have a cycle of many seconds. If you have a critical packet that needs to be communicated frequently, you can get many time slots or regular time slots. So you have a kind of schedule where all nodes are allowed to communicate. This way of building is very static. It's not so flexible. If you have only one node that wants to send something, it can only use its own time slots. There are a lot of time slots empty, maybe, because the other nodes are not really sending anything, maybe. So you need to design the system and the slots and reserve the slots for the worst case. And on average, you will have a lot of unused time slots. So you're not really using the whole capacity of the network. You will get really low jitter because you know that no one will disturb your traffic. You have your own time slot in the whole network, and you're guaranteed that you are the only one sending a packet in that time slots. So you get really low jitter. The other approach of building or guaranteeing response time is to use priorities. So, and that can be used with the more normal networks. You just, all nodes are allowed to send packets whenever they want, but they have different priorities. So critical traffic gets higher priorities. So it's, and this is a thing that the whole network must be able to know this and be able to prioritize traffic as well. So when a packet arrives, they must look at the priority. They must have some kind of identity on the traffic to see if it's high priority or not. And the high priority packets must be sent first. That's the kind of idea here. And then it makes it really flexible. You can actually have low priority traffic that uses all available bandwidth, but you can still guarantee that critical packets will have a higher priority and will be sent first. So the priority-based or event-based systems are much more flexible. You still have guarantees using the priorities. You will typically end up with higher jitter very often. And that's because even if you have a high priority, it might be the case that the network is busy sending a low priority packet, and they very often cannot be interrupted. If you have you typically send large packets all the time to get efficient traffic. And in many networks, you cannot interrupt one packet or one frame. You must finish the transmission of one frame before you can start sending a higher priority frame. And that introduces some delay. And if you have many links, many hops, many switches in the network, you can have bad luck. So a critical packet might get slightly delayed in each hop. And then you actually end up with quite high jitter, maybe. Sometimes the deadlines are not so tight, so then it's okay. You could live with slightly higher jitter, and it works fine. So priorities much more flexible, but cyclic is more deterministic and easy to design and reason about. So this is an example of some kind of combination, or illustrating how you could design something. And this is a quite very common idea used both in wired and wireless traffic. So if you have some kind of network or links, you are sending traffic, you start by dividing up the time in cycles. You need a global clock. All nodes needs to be synchronized to know when the cycle starts. And then you have time slots of a certain length, time slot 1, 2, 3, and so on. And it can be combined. So you have reserved time slots, like in this picture, you have real-time traffic with 10 time slots available to be reserved. And then you have the remaining time in one cycle. You could do all other traffic, best effort. So that's a very common way of combining real-time slots here with remaining traffic. You get a better utilization of the whole bandwidth. So, and when you use time slots, you could, for example, assign one slot to one device here. And then you have a controller that knows that in this slot, it will talk to this device. And in the next slot, it will talk to the next device, and so on. Then you get a guaranteed, at regular intervals, you get a guaranteed time slot here that this device can communicate. And it will be very deterministic and very well, predictable. And you get very low jitter. You send a request to this device and it answers, and it will be very low variation in response times here. So you could get a jitter of 0 here. Yes. In priority-based networks, it's more flexible. But you have this problem with non-preemption. That is, if there is a long packet that is currently transmitted over the network, you must wait even if you have a high priority. And one thing that this time-sensitive networking standard, the Ethernet TSN, it's a new thing, suggested. One thing that they have introduced is frame preemption. It's one of the techniques they would like to, that they have standardized, really. So some switches today can support frame preemption. And that means that when a high priority frame arrives, packet here, it's the ST, the green one, and there is a long audio video, it says here. It's a lot of traffic, but not so important traffic with very long frames, large packets. It can actually interrupt these things. So you create fragments of this long frame, put in your critical high priority frame in between, and afterwards you can continue with this long frame instead. So you are allowed to preempt this frame. That's the technical name for it. And then you actually are able to send this high priority frame faster. When it arrives, you can actually send it almost directly, especially if you have a cyclic schedule. So you know in beforehand that now it's time for a reserved high priority slot here. Then you can actually prepare this fragmentation before the packet arrives. And then you know that now soon there will be a high priority packet, and then you are prepared directly to send it. So you will get very low jitter. If that's really important. If you have a large network with many switches or many hops, it can be important, because if you add a millisecond in each hop, it can be quite a large delay in the end. So for some traffic and for large networks, it might be very important, these things. And how much can the delay in the worst case become? Well, this is an example. If you have normal Ethernet, 100 megabit per second Ethernet, one frame has a maximum size of 1500 bytes. And if you just compute the bit speed here with the number of bits to send, you can calculate that it's approximately 150 microseconds, the time to send one packet. And if you're a high priority packet, you can, if you have bad luck, you need to wait 150 microseconds here before you are allowed to, your packet will be sent. And if you have a large network with like 10 nodes, you can have bad luck and end up with this delay in each node, each hop, and then it will be, well, the jitter or the delay can exceed maybe 1 millisecond, and that's 1 millisecond can be really long time for some applications. But it depends on the application. It depends on the size of the network. So in some situations, this kind of small delays are kind of, well, you don't need to care about it really. If you have a deadline of 1 second, you don't need to care. So it really depends on the application and the network. Yes, so that's really a general introduction to the whole industrial communication area. So I have, there are some ways, you have certain requirements on determinism and real-time requirements, and you very often solve it by having cyclical time slots or priorities. And that's the kind of general background on all kinds of industrial communication, really. So next here, I was planning a little bit to take a look on field buses, and that's the a bit historical view. It's a lot of traditional buses that are used in industry, and many of them are actually really old as well. So I will try to switch the presentation here, And yes, I think, is it the chat window might be visible here maybe. I do it full screen anyway, I think that works. So field buses, let's see now. Yes. So if we remember the picture of a factory or the networks, we have robots and stuff on the right hand side and the economy systems on the left hand side, but now it's down and up instead. So we have the sensors and PLC controllers down here, machines, and then on the factory level, that's the supervision and control systems and maybe economy systems and things like that, back end. And when we talk about field buses, we really mean the communication down here. So it's not the normal local area network or something. It's the buses and communication that has these real-time requirements or requirements on deterministic behavior. That's the field buses. And it's, well, a PLC is very often involved as the kind of controller or computer that you connect things to. It's programmable logic controller or computer, no, control, okay. But it's really an industrial computer made for controlling machines. That's it. But it can read data from inputs. It has maybe push buttons, sensors of different kinds. It takes in input in a lot of inputs, and then it typically runs a program that do something, and you have a lot of outputs. You can control stuff. It could be yes, it could be lamps, yeah, lights, or contactorer, well, relays or switches in some way that you can control. Starting, stopping machines and things like that. It's a normal computer, but they are very often a little bit strange. You program them in different other kinds of languages. For example, you can use ladder diagrams, kind of logic diagrams to program them, and that makes it a little bit, yeah. So it's not, it's quite often not normal programming languages, but they are actually normal computers. So it could be possible using these kinds of programming languages. Well, it's a tradition, and maybe it's simpler for many people. I'm not sure. I think many students have the DIP students. You should have tried these things in some course, I suspect.
Ja, i styrteknikkursen.
Ja, yes. Styrteknik, control course, yes. I'm not sure what you used, but maybe ladder diagram or something.
Ja, ladder diagram.
Ah, that's good. Everyone knows ladder. Maybe. But this picture here, you can see what a typical PLC might look like. There are many different brands and manufacturers, but they will not look at your typical computer, and they are typically very modular and expandable. So you can buy more IO modules and put and expand your system easily. So when you buy a PLC, you get a small thing, but you have a lot of IO modules that you plug in as well. And they are somewhat expensive. Yes, but that's because they can handle a rough environment. they are maybe easier to install in a factory and things like that. So using a normal computer would be quite complex, or a Raspberry Pi or some small computer. So this is more robust in some way. Yes, so a PLC typically works cyclically. So it runs a program over and over again. And it has a cycle of maybe 1 to 40 milliseconds or something. That's when it starts over. And in each cycle, it typically reads all the inputs. It runs a program. It might do communication to operator panels and things like that, but it sets outputs and controls stuff as well. And this is done over and over again. And the programs you create might be like this, a kind of ladder diagram. And that describes the logic really. So if a switch A or B is on, you should put the output on as well, or something like that. So programs can be really simple, and then they are automatically run over and over again to check if this is true. So it's almost as not being need to program anything. Drawing this kind of diagram is like an old electronics people can build their logic using pure switches and wires only, but instead they put it in a PLC and they can think the same way. So maybe a convenient way of programming these things. But since a PLC is very typically cyclic with a certain cycle time, that forces very often the whole system and all communication to actually be cyclic. So it's very common with cyclic systems, cyclic communication. You might have a communication buses that must have the same time slots or everything depending on the PLC cycle. So if you have a PLC cycle of 1 millisecond, that determines the cycle for the whole system and all communication. Yeah. So yes, and the PLC uses typically field buses and to communicate with I/O modules. So that's you can have distributed units far away from each other, and you have a field bus in between. And they are typically old, 80s or something, and manufacturing dependent. All manufacturers in the beginning invented their own buses. And eventually they tried to standardize things, but there are many buses today as well. So it's a jungle, really. Why do you need special field buses then? Well, it's not really about the computer or programming or networking technique. It's more practical reasons. So they make it simple to install electrically. It's flexible modules, simpler to redesign, rebuild, less documentation. It's standardized in some way. Information exchange works in intelligent way. I'm not sure what that means, but it's a good and cheap solution, really, if you want to build communication between different PLC and its devices, maybe. And it's all the ports and connections are standardized, so it's fairly easy to install and make it neat, like in this cabinet here. It's easy to to make it nice, maybe. So yes, that's the reason. And yep, and here you have an example of a modular I/O system. So each slice here is one module that you just add on here. And you can also have modules far apart, and then you have some kind of field bus here. And it's called bus since you have many devices connected in logically on the same wires almost. So when you send something, it might be in a real bus, all the units here will receive the same data, but only one will act maybe. You're addressing the data to different modules here. Yes, so yeah, but when do you need field buses? Well, they are good because they are deterministic. They have good real-time characteristics. So it's a safe choice if you have critical traffic. And very often when you buy a PLC, you must use a certain field bus because that's the standard for a certain manufacturer or something like that. So if you build a system with PLC and some I/O modules or operator panels, robots, you actually are almost forced to use a certain field bus, even if you don't like it. And they can be good. Yeah, it's easy to redesign but the range is not very long. It's designed to be inside maybe a factory or something, so it's like 200 to 500 meters maximum. Yes. Oh, talking. That was a slight introduction of field buses. I will do some general communication things here before looking at an example, but I think we should have a break. Let's see. I do a pause of the record. Yes, now. Yeah, hopefully we are more clearer in our heads now after a break. We'll see. But I have been introducing some motivations behind field buses and also taking a look at the PLC. But the remaining here, it will be an example of some field buses and some practical, it's more examples actually. But first some theory again, or maybe some models. So I think many of you are familiar with the OSI model. And that's the general network technology model for how you can look at networks and also the protocols used. So, and you very often divide it up. The OSI model is 7 layers, but you quite often use some of them only. And most common, it's the physical layer and data link layer. Physical is the electrical hardware. Data link is responsible for actually getting data over a link and point to point. And network layer is in a larger network where you have multiple hops and you need some kind of routing. And then up here you have, well, at the top you have the application level. That's really applications talking to each other. And when you talk about field buses, it's really only a few of these layers that's standardized typically. So the different field buses are mainly layer 1 and 2, but sometimes it's actually some data exchange standards concerning layer 7 actually as well that you can find. But almost always it's only level 1 and 2 here, layer 1 and 2. But there is actually a standard on layer 7 or something that helps applications communicate, and that's the OPC. It's a one successful standard actually. So it's a stands for Open Platform Communication, and it's a way of clients talking to servers. So the PLC might, for example, have an OPC server inside, and then you can quite easily have a, if you're in another system, you can it can be an OPC client and easily get updates for some measurements or values from the PLC, and it's really a framework of some kind for communication and also convenient software libraries. So you can, when you write your program in the client here, it's very convenient to, you can subscribe to new values automatically, and the server will send it regularly to the client. So yeah, so there are some nice standards actually that makes data interchange easier. But this OPC is actually independent from the actual field bus technologies and things you're using down here. So it's a general technique, but very often built into, for example, PLCs and things. Yeah. So otherwise, a little network basics. You have something called topology. That's how you interconnect different nodes. And it's good to know about some of the good and bad stuff about how you should connect things. Different buses uses different ways of connecting things. Like in our normal global internet or local area networks, it's very common with these star topology. You have a central node, switch, or a router, and you connect your nodes or clients each individually to this switch or something. It's the same, very often the same in wireless Wi-Fi or something. You have an access point, and then you have all the clients connecting to it. So yes, it's easy. Yeah. So what's the good stuff about this? It's good from a failure point of view. It's less risk for collisions. You have a coordinating node in the middle that can control the traffic, especially if you are if it's wireless. You are alone on your link, so if it's duplex, that means that you can send traffic in both directions. You have the whole link for yourself, so there is no collision possible really. And you can easily disconnect one node, and the remaining continues to operate. It's some bad things as well. It's more cables, and it's a central point which is kind of vulnerable here. If and maybe a bottleneck as well. So the switch or the hub here needs to be good enough to handle all traffic. a more cheaper network is a bus network or multi-drop network. There you have all nodes hear the same traffic in some way, and that saves cables. You don't need so you have only one cable maybe, and then you have a lot of connections where the nodes enter. Yeah, so it might be easier to install or redesign, and you might save on cables sometimes, but you get less capacity. All nodes needs to handle one common bus here. So so that's a drawback. And if you get if you break a cable, the whole system will stop typically. So it's not so fault tolerant. And actually, yes, Wi-Fi, wrong of me. Wireless communication is really like a bus because everyone is in the same space. But logically, you have a controlling node when you do Wi-Fi. But it's actually really a bus in our space. So these are two very simple, basic ways of connecting nodes. But one of the more common ways of connecting, especially when you have more critical system, is to use a ring network. It's almost like a bus sometimes. So it could be the case that you have one large cable that all nodes connect to. But a very important thing is that it's a ring. So even if you get an interruption, if you have a link that goes down here, there are always the opposite direction that you can send traffic. So you can reach all nodes even if one link goes down, and that's really good because you need that fault tolerance sometimes to be able to get better reliability. So ring networks are actually very common to use if you have more critical systems. Some other nice terms to know about is simplex, half duplex, and full duplex as well. It's how you can communicate. So simplex, then it's only one node that can send, and like a master or slave, for example. So if the master is sending something, the slave cannot use the link. So it must take turns. You can only send in one direction. Oh, yes, simplex is only one direction. Half duplex, then you take turns. So one at a time in the half duplex. But full duplex, you have double links in some way. So you can communicate at the same time. And well, what's our wireless transmission? It's very often half duplex because when one transmits, the other nodes cannot transmit at the same time because then they will interfere. If you have cables, you can easily get full duplex because it's only a matter of having double cables in some way. You also distinguish between serial and parallel communication. Serial is really sending all the bits in a telegram one at a time, and you have few wires. You have typically only two wires, one signal wire and one ground wire. So, And if you have full duplex, you might have 3 wires, maybe. 1 receive, 1 transmit, and 1 ground. But if you do parallel communication, you can have really a lot of wires. So you send many bits at the same time. So you might have 8, 16 or more, plus the signal ground wire. So then you get 8 times as many bits in the same time. So parallel used to be really a fast way of communicating, but actually more and more communication today are serial, because you can actually make it work simpler with higher frequencies when you do serial. So serial very often wins over parallel today. So a very old field bus actually is the normal asynchronous serial communication, and it's very old. It's very widely used. Recent 5 or 10 years, it has disappeared more and more on our computers. But if you look at computers 10 years ago, almost all laptops, computers, all systems had these RS-232 ports. It was used to connect mouse and keyboard, and also as a general communication technique for all kinds of systems, and it was widely used in industry. So you have a transmitter and receiver and a ground. It's a very simple way of connecting systems, and you just yeah, so it's 3 wires and you get communication. So it's very easy. So it's introduced already in 1962, maximum 15 meters, but well, that depends on how fast you go. But yes, they are. This is the actual most common, but on industrial systems, this is there were a lot of other standards as well used. So 2 other examples are RS-422 and 485. They were able to do longer distances and had more, well, better electric characteristics in some way. So, for example, this one was full duplex, but a bus network. The basic serial here is only point-to-point. But in this system, you could have many nodes electrically connected to the same wires here. And that's very convenient if you want to reach a lot of, for example, slave nodes or sensor nodes from one master node here. So you want a bus network. Yes. So it had separate transmit receive and also no common ground. So it was isolated. So even if you had different voltage levels in different ends of this network, it works anyway because it was electrically isolated in some way. Yes. So, and then we have the 485, which is actually used in a commercial field bus called Profibus DP. And it's still quite widely used. And this is also a bus network, and you can have up to 32 slaves here, or receivers. So, and you see it's only 2 wires, so it's typically cheaper in some way. But it's half duplex, so typically the master asks a slave of something, polls the slave, and then the slave are allowed to answer. But they need to take turns. they cannot communicate at the same time. Okay. So serial communication are very common. Actually, our normal Ethernet is also serial communication. And then we have the CAN bus as well, very common inside cars, but also in automation. You have the CAN open and DeviceNet in factory automation. It's also half duplex. It's a bus network, 2 wires, and you will learn more about the CAN bus in the next week, actually. Next week, yes, with Eric. But Ethernet is actually a bit interesting as well, because it's also a serial communication protocol. So, and you have 2 wires for receive and 2 wires for transmit. So it's full duplex, but it's not really a bus network as we normally use it for local area networks and things. We typically connect point to point to a switch, but there are many ideas and field buses here that is based on Ethernet, but users have remodeled it as a bus or ring network. And yes, it's some examples are Modbus, EtherCAT, Profinet, PowerLink, and Ethernet IP, and there are more. There are more bus field buses that are based on Ethernet here. Okay, serial communication are really common, so might be interesting to see how it works in more detail. Very often you have, when you do serial communication, you have bits that you send. You have maybe eight data bits as a byte, and you send them one by one. That's the idea with serial here. But for example, when you do asynchronous serial communication, you need some way of telling the other end that now I start to send, and you have a start bit typically that signals that now it's time to start receiving all the bits in this byte. And in this example, you have a start bit, and then you have 8 data bits, and then you have a checksum parity bit that you can use to detect errors. And then you have a stop bit that kind of tells the receiver that this is finished. And then you have a neutral voltage level here is the idle level, which means that it's in between the different data bytes or octets here. Yeah, so it's quite common. Yeah, in normal you have the least significant bit. So it's sent first, so it's really backwards. So if you read it, it depends on how you look at it. But if the time goes here, this is the first bit, data bit that is sent, so that's the least significant bit. Parity is a very simple idea. So if you have an even parity, you should have the total number of ones here should be an even number. Then it's no error. So if you get accidentally an error, so 0 goes to 1 or 1 goes to 0, you will discover it because the number of ones here will not add up correctly. So that's the idea with the parity. Parity, that's the wrong spelling here. Yes. Each individual data byte you can send. That's fairly simple, but to get a meaningful communication, you need some higher level protocol actually. It's very often more than 1 byte you want to send, and then you need kind of group data together in a frame or larger packet. And it's very common that you have multiple data bytes here. And then you will typically end up having a header and a trailer or something, some overhead administrative data and bytes to signal that, yeah, start of transmission here. STX means that now there is a new packet arriving. And if you have a bus network with many receivers, you might need an address that it's the node number 49 that this data is supposed to be sent to. And you very often have a number of data bytes as well. So you know the total size of the whole packet. And then you have the data bytes. You might have an extra checksum value to be able to detect errors over the whole package. And then you have an end of transmission as well in the end to signal that the frame is complete. This is a simple way of kind of making a package or a whole frame. Could you skip the number of data bytes? Well, maybe. You could just receive data until you see some kind of marker that this is the end of the packet. But then you end up in trouble. For example, if you use 1 byte 03 here as the end of transmission, it might be the case that one of the data bytes here also is 103. So you start complicating things when you skip kind of the number of data bytes field here or something. So these are very common ways of designing a package. You have a start flag of some kind that marks the start of the thing. You have an address and number of data bytes. It's very, very common. And a checksum is also very common to have in the end to detect errors. Very often, or sometimes, you have text messages sent, and then you typically use some coding. So you have the ASCII table, for example, where if you send the number 50 as 1 byte here, it actually maybe mean the letter 2 or letter B, A, or C or something. So if you want to transmit text, 1 character is typically 1 byte. If it's not a modern coding with UTF or something, where you can have strange letters as well. So yeah, so this is an example of communication protocol. So here are some field buses, and it's a little bit of a jungle, and I don't think if you work for many years in the automation area, you will start learning more and more about these buses. But here we will only look at 1 or 2 examples. And as an example, it will be more about Profibus and also a little bit about EtherCAT, and then you will look at the CAN bus in 2 weeks as well. So you will get some examples of field buses here. And they have different, well, there are field buses in this level here, but some of the buses are actually useful on control, cell line, or factory level as well here. So it differs slightly. So, but yeah, so, but that's really the manufacturers that thinks that this bus should be useful all the way up here. then it's not for certain that it's used actually. It might be used down here only, and then you have normal Ethernet-based local area network technologies up across a factory maybe. Some of these are stationsbuss. It means it's a special standard for the energy sector, like electricity distribution networks. So it's not automation industry. But many of these protocols are used in many different industry segments. So it's not only automation factories, or it can be other industry as well. Well, Profibus as an example here, developed by Siemens, and that's typical of this kind of bus. Each manufacturer invents their own bus, but today it's very widespread and used by others than Siemens, but Siemens are the one that still, well, are the main interest part in the standardization and thing. There are many different variants, but the DP is the most common one, and uses this serial communication RS485 as the most usual thing. But Profibus has also been extended with a Profinet that uses actually Ethernet hardware. And that's a later invention, because Ethernet hardware, that's our normal local area network hardware. It's quite well known and very popular and cheap. So all field buses have almost adapted and tried to evolve into using Ethernet actually. And Profinet is one example of those things. Yes, Profibus. So a Profibus topology looks like this. It's a bus network. You have a master and you have a lot of slaves. It might be possible to have 30 or 30 slaves maybe, or something, station, yeah, something like that. But you can also use repeaters to connect more segments. So you can have very large networks, maximum 126 nodes. And if you have a lot of different like sensor or modules, this is very convenient. You don't need to build large networks like in a local area network with a lot of switches and ports and things. You just have one bus wire where you connect everything. So it's convenient. One thing that is a little bit interesting is that it says termination here on many different things, and it's a very special thing when you have long buses and long wires. You typically need a termination resistor, and that's very common when you have bus wires in many different buses. So the problem is that well, it's some kind of electromagnetic characteristic that if you have different impedance or resistance in the wires compared to the receiving end or node here, you will get a reflection. So, and it's that's complex, but it's a general rule that you sometimes need a resistor to match this resistance 120 ohm here. It should match the wire's impedance in some way. Then you don't get a reflection of the signal, and then you get a nicer signal. So this is a nice signal if you have zeros or ones maybe here in some way. If you get reflections, you get a disturbed waveform here, and something called ringningar. Oh, that's a strange word. that so without these termination resistors, you will get disturbances, and that could actually make the bus stop working. It's only needed typically at the end. Sometimes the nodes sometimes have a very high impedance, because that's the normal when you have inputs, so they won't be disturbing the wires at all when you add more nodes. But in the end, when it ends in, the wire shouldn't end in an empty space. It should have this resistance at the end. For Profibus, it typically looks like this. You have two wires, and this is the way to terminate the wires when you're running out of nodes. So nodes are connected directly in between, and that's no problem. But if you have an end that's kind of not connected to anything, that's not good. So you need this kind of resistors at the far end. So if you install Profibus stuff, you have a special termination at the end of the wire. Profibus is a kind of very, it's this half duplex, and it's very kind of slow. It has a controller master here that asks each node one at a time in a cyclic manner. So that means it has a large cycle, and it has some kind of time slots actually, that when it asks a node for data and the node responds. And yeah, so it's not super fast, probably. Yeah. So there are also a lot of different versions here, and this is quite typically you start with a simple cyclic communication pattern and poll requests, and this is the basic. The PLC might ask 10 different sensors, one at a time for some kind of sensor value, and but when you build this kind of system and start using it, you typically find that, oh, it would be nice to have some extra possibilities in this network. And the thing that you end up needing is all the administration things. For example, you need some acyclic communication, and that might mean that you need to program sensors, debug sensors. You need to load new programs or firmwares in sensors. You have this kind of managing or administration traffic that's not part of the regular operation. So they have support for this kind of acyclic communication. That is, might be larger chunks of traffic, but not this cyclic, regular, real-time traffic. Yeah, and also you have event controlled. That's more of a priorities, leaving these cyclic slots, but having the possibility of events instead, and that might be alarms or things that happens rarely, not in this cyclical way. So these are versions that really handles all kinds of different communication patterns. Yeah. Okay, time flies. Here's a comparison between Profibus and CAN. I don't think it's so interesting, but CAN is kind of slow, Profibus probably faster, but there are so many different improvements on the protocols and versions, so I think it's hard to say that one wins always or something. So I'm not sure that's the case. but we see here in both cases that we talk about kilobits per second. It's not gigabit or megabit, but sure, here it's megabit actually. So that can tell you something about the typical speeds you use here. So it's very often kilobits per second, and that's very often quite enough. You are not reading so much data when you just want some sensor values. Okay, so time is flying here. I have some slides more, but yeah, this is really repeating these things about real time. You have soft and hard. And normally when you look at a system, you can design systems depending on if you have soft, hard, or don't need real-time requirements at all. And for these normal systems, you can use normal TCP/IP, normal Ethernet. You don't need to guarantee anything. And the delivery time or reaction time is really unpredictable here. For soft real time, you can use maybe traditional field buses and Ethernet. And for hard real time, you need maybe special equipment. And you have more tighter timing deadlines. But when you look at Ethernet, they have a classification that's quite interesting, I think. Many tries to adopt Ethernet hardware because it's cheap and existing. And you could then classify different things according to non-real time or soft real time or hard real time here, ABC. And if you do no real time at all, you can use standard hardware, standard internet protocols, TCP/IP. You don't really need to do anything fancy. It's a normal network. But still, there are some application or frameworks that helps you for these field buses. So there are a lot of Profinet and things that you can still buy, but it's really standard internet technology in the bottom, but you get some extra frameworks or libraries. But then you might have a little bit more real-time requirements, stricter requirements. You have replaced typically TCP/IP with your own protocols, but still uses the same hardware. And when you have very strict requirements, you need also special real-time hardware. So you cannot use maybe normal Ethernet hardware. You need special chips in some way. Yes. And I'm a little bit scared of having too many slides here now. So time is 15. Yeah, the remaining was some slides about EtherCAT as well. They use a ring. You can build a ring topology, which is quite fancy. And then you have some problems with long wires, disturbances, interferences with different things, and some solutions for that. So I think I will repeat this next time. I think I shouldn't be doing too much overtime here. So see slight continuation next time. Otherwise, see you next week here.